Hello.
Yeah, Deep.
Um, I don't know. I think somebody was calling me. Um,
Calling us like on
um,
the meet.
on here, I think so. I don't know. I think I heard. Could you stop the recording for now and you can start when you start the presentation?
No, we're just about to start right now.
Okay, okay. All right.
So let me just share my screen as well. Can you all see my screen?
Yes, it's visible.
Okay, fine. So we're about to start in a minute. So today's recitation will be on convolution neural network and will be held by me, Ananya Malik, and Jash Mehta will be joining us for the second part of this recitation. So I be I believe Swapnil yesterday covered padding and stride. If somebody could also like confirm that. Can you all hear me?
Yeah, we can hear you.
Yeah,
Yeah, basics here and are covered yesterday, so yeah, you can continue with that.
yeah.
No, good to know.
So basically, in today's session, I'll be covering the basics of CNN. So it most probably be a revision of what you all did yesterday, and we learned to code Lenet, which is the first CNN architecture that was established by LeCun in 1998, if I'm not wrong. And Josh will be covering the modern CNN's part. So, in case you have doubts, we'll have a doubt session at the end of this. Hence, so you can hold it out till then. In case you ever feel like I'm going too fast or too slow, or can't understand what I'm saying, please then stop me right there, and I'll cover that part again. Um, so you all know what CNNs are, that is convolutional neural networks. They work similar to what regular nets do. They have the same basic features. They contain weights, they contain biases, we use a loss function and we use an optimizer. But apart from that, there's also convolution. There are different layers to the convolutional neural networks. One is obviously the convolutional layer. You've got the pooling layer, the flattening layer, or the fully connected layer, and which we will deal with this notebook. So basically, we'll start from the very basic, and we'll be able to build up your first CNN network. The uses of CNNs is basically synonymous to image classification and anywhere in image processing in deep learning. CNNs are always used. I don't think there's any application in image processing where CNNs people don't use CNN. I think that's become their first approach. It also finds uses in NLP. So the data set that I will be working on with you all today will be on the MNIST data set. It contains 60,000 training images and 10,000 testing images. So we start with so because we're using PyTorch, we start by importing transforms. We'll find out the use of transforms in this cell only. Um, MNIST, like because it's such a popular data set, it is available for download using an API right here with the in the Torch database as well. So we can just import it from there. So we set our data set, we call it the train set, and we download from the data sets here. We download the MNIST data set. Because we're using Colab, we're going to be storing it in a root directory called data. And because we're here first, we're going to train the images and then we'll test. So we're going to train, put test true, and we're downloading the directory, so we're keeping it true. And now with transform, we say transform is equal to transform because we want to. Now we know images are dealt with in pixels. I think that's what some you all know. that Swapna must have covered yesterday, that images are dealt as numbers as numpy. So we have to convert them to tensor, and we have to also normalize them. So this transform function is performed here, where we're normalizing the median and the standard deviation, and we're converting this numpy into a tensor. Then we set the batch size to 256. That is, we will be loading about 256 images at every on every data set. So we call it the train loader. We load this data into this train loader, and from the data set, with the batch size 256, we keep shuffle is equal to true, which means that every time we call the train loader, the GPU will give us a shuffle any random set of images. It won't be the same, or it won't be in a particular order. So we just like run this. I should have done this before. Sorry. Um, it will now download. So meanwhile this is running, you can just like come up here what this does. So now our train loader is an object. We iterate over this object, and we store that every iteration into data iter. From the data iter, we can, we do next to be able to access every element, and which is then stored into an array of images and labels. Once this is loaded, I'll run this, and we'll be able to see the shape of the image and the shape of the label. So each image has a label attached to it. Just give it 2 minutes. I think it takes a little while downloading. Okay, while this is running, I think it just gave an error beach before. I don't know why, but I will just like while it's downloading, I'll just like continue explaining the concepts. So now it loads, like I said here, it takes the train load as an object and loads it and iterates through data item will iterate through the elements of this object. This next will be again used to iterate over it and will be able to access using images and labels. We will be then able to see the images dot shape and labels dot shape. Now that's so because we're taking one object with 256 batches of 256. Once this downloads, I'll be able to show it to you that this will have a shape of 256 images, and even the labels will be an array of 256 labels corresponding to each image. Again, here it will be able to load the image. Here we'll be able to see a single image as an example. This is a plotting function that we're using to compare the images. We'll be using it to compare. It doesn't really have any sense to what we call our current code. Um, So before we move on to implementing a part, again we're using a GPU. We can, because it's kind of it's a simpler network. We can work this on a CPU as well. But just to show you, using a GPU, which will be assigned to us by Collab. Here now, while this is running, I can show you what convolutions are. So now basically convolutions in this layer do actually end up working as cross correlations. We have our input as this is our input matrix. This is a kernel which will be convoluted over this input image to produce an output. And the reason why this is done is it's used for computational efficiency, where we will be able to decrease the complexity by reducing the size of our input. So, for example, here we have a matrix given as 0, 1, 2, 3, 4, 5, 6, 7, 8. When this is put over a kernel of 0, 1, 2, 3, so how does this work is it will multiply, it will do matrix multiplication of sorts, where it becomes 0 into 0 plus 1 into 1 plus 3 into 2 plus 4 into 3. This will form one part which is like 19, so become 1 plus 6 plus 12, that's 19. Similarly, it will then this blue will move on to this part, will become 1 2 4 5 into 0 1 2 3, which will give me 25. Then again 3 4 6 7 into the kernel, which will give me 37, and 4 5 7 8 again into the values of this kernel, which will give me 43. So using a kernel of size a 2 by 2 a 2 by 2 filter on a 3 by 3 image, applying a 1 by 1 stride, we're able to reduce the output to a 2 by 2 output. So yeah, I think this is done. So we can I'll show you all what I explained earlier, where we get the shape of this image, which is a torch. Now, because it's an image, the torch requires it to be a it's a 4-dimensional tensor. It's a 256. The batch size is 256. One is the channel, that is the which is because our images as we see here are grayscale. So one is the channel. It's the size of this image is 28 by 28, and the label, the shape is it's a one-dimensional tensor, which is a 256. So there are 256 labels for every for 256 images. Then we see this image. Now this we have taken any sample image. Now again, because we shuffled it, every time you rerun it, we will get a different sample image, and we've run our plot function. Now we assign this as a sample image. We see that we have done dot reshape because, again, as we know, an image is a numpy. We want to convert it into a tensor. So now we come here. Now we give it, we've assigned the GPU to it. We look at, so we've been assigned to Tesla T4. This is the amount of memory available and what our usage is. Like I explained, our convolution, this is how convolutions work. Now we come to defining the cross correlation, or basically the convolution. Here we have X we take as our input image, K is the kernel, which will be computing over the input image. Height and weight is the we assign the shape the values for the axes of K. Now we create now we take Y as an we have X as the input, Y as the output, and K as the kernel. Now because Y is the output, we need to define its size, but it will be an empty matrix. So this torch, it will be a tensor of zeros. We know, as we see here, Y is the shape of Y is equal to the shape of X minus the shape of minus the width. Suppose the width of the of X minus the width of the kernel plus 1. So that's something that we do it here. So X dot shape of 0, that is 1 over 1 axis, minus the shape of kernel on the same axis plus 1, and and shape of X on the vertical axis minus the shape of the kernel on the same axis plus 1. We now iterate over we create over both the axes, that is on the horizontal axis and the vertical axis for output, and we assign Y of j as X is plus H. That will give me up till that basically doing this computation that we showed here. Into K is the kernel, that is of we're multiplying, and we sum it because we're like I said, it was 0 into 0 plus 1 into 1 plus 3 into 2 plus 4 into 3. That gave me 19, and we return the value of Y. That will be my final output image. Now we're just taking an example of a convolution here, where we take again that the similar thing that I showed of the example Upar, where it's 0, 1, 2, 3, 4, 5, 6, 7, 8, and the kernel is 0, 1. It's kernel the 2 by 2 kernel, and our image is a 3 by 3 image, where we finally get our tensor as our output image Y as a 2 by 2 image. Now this was when we have used the correlation function. Now Torch also provides a convolution function. Now to define a convolution function, we require there are two steps. One, you have to define the kernel, and the second set values of the kernel. So in defining the kernel, we have the conv2d function. We assign it by using by using neural nets. The first one is here stands for the input channels. That is the number of inputs that I'm getting. The one is output channels. We define the kernel size for, like we've done here, kernel 2 by 2. It's a 2 by 2 kernel, and bias we keep it as false. Again, here we assign the values of the kernel. That is again the same values that I've used here. I can do it here using the conv2d function, where we do it, keep it as 0, 1, 2, 2, 3. To make sure this is a tensor, we keep the data type as torch.float32. And this is again reshaping is to make sure the size of the kernel is 2, 2. And this is because it's a tensor, it requires 4 inputs. So that's why we've kept it as 1, 1. Then we see we get the torch size, that we see that we get the our kernel is defined now. And when we put it on our X, that was our original image here, working on this image, we're able to get, and again we use reshape here to convert it into a tensor. We're able to get the final output of 19, 25, 37, and 43, which is similar to the function that we defined. Now this is what we did on our on an image that we have defined. We'll do it again for our test image from our MINS data set. So we again define the kernel shape at 1, 1. We define a kernel size here of 1, 2 instead of doing 2, 2 to make our life simpler. We keep the bias as false again. We then again go set the values of the kernel. Now again, we are giving the values of the kernel. Now you will see when we go ahead, you will see why this is an important step. We keep it as the random's value of 1, minus 1. Even though they're not random, you'll see why we give it as 1, minus 1. We again assign the data type, and we reshape it because this is an image. We reshape it to be a tensor. We reshape it to be a tensor using 1, 2. We have again then applied the conv2d function using our sample image reshaped, and we plot the two. So we see, you can see this is our original sample image, and this is the image that has gone through the convolutions. Now you see these black lines. So the reason this comes is because it is able to detect an edge. Now the reason we kept our kernel size as 1, 2 is because it's then able to detect the edge on the y-axis, on the x-axis. We see that our kernel's convoluted image size is 1, 28, 27, with the size is obviously reduced because it undergoes convolution, and the image size is 28, 28. Now I know Swapnil also did padding, so I won't go much into details on how padding works and what is the use. I mean, we've provided like resources at the end if I want to even go through that. Then we now the use of padding again comes when you're going to assign a padding to the kernel. Now we've copied the same function as the kernel that we defined here. Just now that we're attaching a padding of size 0, 10, which means there will be padding along the y-axis. Similarly, we keep the same set the same values of the kernel to be 1, -1, which means we're performing edge detection here as well. The same steps as before. Again, so you can see here, it is able to detect the images, and also these vertical lines are created because they are able to detect the edges in the image. So that's what the padding does. Again, because now I think you also would have known padding doesn't change the size of the image, hence the size remains like similar. Then again, we come to stride. Now stride is how fast, basically, in how many steps can you move within the matrix. So here in our case, we define a stride of 1, 2, which means on the x-axis it is able to move on a stride of 1, but on vertical axis it's able to take a stride of 2 steps. The rest, everything we've kept it similar. Now we're able to see this. This is again This is the input image. This is the output image, and now we also see that the size of the output images on the x-axis has reduced in size because we're moving twice as fast. Like we're taking 2 steps at a time. So that's why the convoluted image is shrunk in size. You will see here also the torch size remains like for the sample image is 28, while for the convoluted image it becomes 14. Now we've got the max pooling. Now I'm not sure if he's covered it or not, but I'll just like go over the basics of it. What max pooling does is within our pooling layer, our input, when you provide a max pooling layer, it will take the maximum of this blue box. So here it will take 0, 1, 3, 4. So it will take 4 as my number. So in 1, 2, 4, 5, it will take 5 as a number, and that it will return that as the output. So again, max pool 2D is provided as a function within the is provided as a function by PyTorch, so we don't have to like write code for it. Like now, I will. This is the pooled image, and like you see, because we use the 2 by 2 max pooling layer, the image shape has reduced from 28 to 28 by 28 to 14 by 14. Now we've been able to define a kernel and understand the different layers that have gone in creating that we can use using this kernel. So we've got max pooling, padding, strides. But now we come to obviously we won't be able to provide a layer like that it won't help us if we're already providing a kernel to the machine. Our machine needs to be able to learn the kernel, and So first, I will be defining my kernel for my sample images. I will be defining the kernel. I will be using a similar kernel that I've defined above. And but I'm using torch.nograd. Now, one of the reasons torch.nograd is being used is because we want the kernel to be able to, we want the machine to be able to learn the kernel. We don't want to give the a pre-learned kernel to the machine. So it does not, by using nograd, it will not remember the gradients of remember the gradients of this kernel. So we have x as our input image, y as our expected output image, which is taken using this with this definition. And now we'll see how to learn the kernel. So now again, like in the two steps of defining a kernel, first you have to define a kernel, and then we assign values. Here we won't be assigning values because we want the kernel to learn. We won't assign values to it, but we have to define the kernel. So we create a kernel called conv2d using the conv2d function from PyTorch, and we give one as the input channel, one as the output channel, the kernel size as 1,2, and bias as false. We take x and y. X is my input image, y is my output image. So x dot reshape and y dot reshape, because that images we want to convert them into tensor. We have a learning rate as 3 minus 4. Now you can experiment and try to find a learning rate that suits your task more. This is what the scientists were able to get to. Again, we iterate over this over around 100 times. Again, this is again an experimented value. We'll see if we require more or we require less. Now we apply this kernel on x, that is y hat. We assign this as our temporary kernel and assign it over x. We calculate the loss, that is from y hat minus y, that is and square it, because we want to compare the from the expected output and the one that we're getting in this loop. We set, because we're going to backprop it, so we have to set the gradients to 0. We calculate this, we backprop the losses, calculate the sum, and we are able to get the updated kernel weight. And we finally print the loss function for each of the batch size. So we see it starts from 68, goes down to 0.027. See. And you see, with almost the tensor learns almost correctly as what our expected value of kernel. We wanted it to be a 1, -1 as a value for edge detection, and we're able to get something that's pretty close to 0.98 to -0.98. So it's a pretty close value. So this was understand. Now let's just recap what we've done. What we started with was basically trying to understand what is convolution. We were able to write our own code for a convolution. We studied the MNES data set. We then understood what a convolution using torch does, how to define a kernel, how to set the value of a kernel. We went through padding, where we were able to define we were able to add padding to our kernel. We were able to add a stride. We were able to define a max pooling layer, and then finally we learned how to make a kernel learn. Now we look at what LNet is. It's again like the first architecture, like I said, was proposed for a CNN, and this is more of the compressed network of how an LNet works. It takes a 28 by 28 image. It puts it into a 5 by 5 convolutional, which takes has an output channel of 6 with a padding of 2, which then goes into a 2 by 2 average pooling layer with a stride of 2. This goes into a second convolutional network, which is a 5 by 5 with a output channel of 16. It is then inputted into a 2x2 average pooling layer of stride 2, and this is called our convolutional block, and this is called our dense blocks. Now, why are these called dense blocks? Because they are fully connected layer that are connected fully connected layer. While here is where our convolution, that is the reduction in the size of our matrix takes place. Um, so let's try and implement this structure from what we've learned. So what we use is class net, which is a predefined module in the network. We initialize it so that we can get like all the properties of this class within our definition. Now, to define or to create a network, basically there are two steps. One, we have to define or initialize all the kernels that we require, all the layers that we require. And second is when we have to actually arrange into the order that we require. So first we will define convolution layer 1, that is this layer, which will be a 5x5 kernel with an input channel of 1 and an output channel of 6. So it has an input channel 1, output channel of 6. My kernel size is a 5x5, we can just write it as 5, and it has a padding of 2. Then we define the average pool layer, that are these two average pooling layers, where we're taking a kernel size of 2 and a padding of 1, and a stride of 2. We don't have a padding here. Then we define a convolutional, because it has a different output channel. We define the convolution layer 2, in which we have an input channel of 6, an output channel of 16, and a kernel size of 5x5. Then we have our fully connected layer. So now the output of this second convolution with the average pool is what goes into this first fully connected layer. So that is why it has an output channel of 16, which is the same thing as here. Is 16, and 5x5 comes with a kernel size here. And then finally the output channel of 120. Similarly, we have the fully connected layer 2. Again, these are linear layers because they're fully connected layers. So we use linear. This is again where you take an output. The input channel is 120 and the output channel is 84. And a fully connected layer 3, where we take the input channel is 84 and output channel of 10. So what this means is that giving an input channel of image 1, our final output will be a linear array of length 10. This is the structure of these are the kernels that I require to set up my LNet network. Now, using define forward, we will now be able to define the order of our network. So now I think if you all have in the previous recitation, you all must have been told, and I'll just say after every layer we require an activation layer. So when we define our first convolutional layer, we have so here we take input as X, that is our input image. We give a convolutional layer conv1, which is then sent to a activation layer, which is the sigmoid activation we're using, and then goes in that this is then pooled using the kernel we defined here. So this completes these two layers are completed in this first function. Then this X is then given to the second line, where we put it when we give it to the second convolutional layer, which is then given to the which is then an activation function is applied over it, and is then given to the average pooling layer. Now, the output of this second X is the output that we get from our convolutional block. Now, because it is a 2D image and our fully connected layers they're linear layers, so they needed to be converted into a 1D array. Hence, we use x.view, or you can use x.flatten to flatten this. -1 and 16 into 5 into 5 is my size of the is my input channel into my fully connected layer. This again goes into the fully connected layer, over which we perform the sigmoid activation function. goes into the fully connected layer 2, which we perform the sigmoid activation function, and finally we return goes into the fully connected layer 3, where we do not require to perform the sigmoid activation function, and we have the final output as final output, which will be the 1D array out of the fully connected layer, which will give me 10 values. We run this. Okay. So now we also have to define the loss and optimization algorithm to train our network. We define our loss as we take the cross entropy loss, and we take the sorry, I think I got
Hello, Anand.
disconnected. Yeah, sorry, I got my mic muted. Okay. Yeah, so we take the stochastic gradient loss as our optimizer. Again, we take learning rates as 0.5 and the momentum as 0.9, which we pass these parameters into our network. Again, these are values that have come through experimentation, and you all are free to experiment on it and find what works best for your task. Now, like we said earlier, this task can be performed as on the CPU, but we're showing you how to perform it on the GPU as well. So the device that we had assigned a while back here, we're assigning using two devices. We're assigning the GPU to our task now. We're basically sending all this network to the GPU. So now our network contains the Conv2D layer, the average pooling layer, the second convolutional layer, and the 3 fully connected layers. Now for training it, basically we will train over the data set multiple times. Each loop is called an epoch, and then we we load the data, that is the data set that we have initially defined. We load each of them into the network into the GPU to load our data. So we send our inputs, that we inputs and the images and labels, to the device. We set it to 0 grad again, because we are using backprop. We need to assign zero. We just need to assign, like, clear the memory off. They should not remember it in the further steps. So then we assign the optimizer to 0 grad. We now here we'll do the basic out of any deep learning network, where we will take the inputs, we will calculate the loss, we'll backprop the loss, and then we'll go over the optimizing steps. So I will keep it on for training. So now it's finished the training, and I will. Now you see it is able to replot our sample image, which is what we used as its number 0, and it predicts the answer also to be 0. Now, before, like, I will show an extra step here, and that is, okay, let's just do this part. So now you see here, it gives me 10 values. Now these were the same 10 values that we get out of the last FC layer. So that's how, that's what, so if you were confused what the final output is, it's these values. Just to show again, it gives me the output 0, and we see how much memory we're using of our GPU again. And that is basically how we have constructed LNet architecture for constructing your very first CNN. So till now, does like anyone have doubts? If you all have, you can like ask me right now, or we'll keep it till like the end of the session. So now, do you all know what batch normalization? Have you all covered that previously? Okay, batch normalization isn't covered yet. Okay. So basically, I'll just give a basic introduction, which I think will be covered, I think, even in the lectures. Later, when you all will be covering with, I think, with modern CNNs. Basically, the idea of batch normalization comes when we understand how much like data we have to use and how to pre-process that data. The challenges that arise with like training a machine, training models and training neural networks. Number one is that we have to make choices regarding our data. So there will be we don't know what data we'll be getting, so we need to normalize it to a part where they're not producing two very different extreme differences in our values. So this so to get them to a similar scale is why we require normalization. In For CNNs, we see that when we train the variables, may take values of varying magnitude, that which may cause a drift. For example, some might be on an extremely high positive, while some might be on very low negative. So to avoid this drift in the values, we require even within the layers, one layer might produce the law may produce a value that is extremely high, while the other may produce very low. So we need to be able to get not just the data within on a similar scale, but also on these layers. And also, there's overfitting is a problem that we know. So to be able to reduce that is where batch normalization is used. In CNN, we see batch normalization is used in all layers. In here, will be applied after every convolutional layer, that is the conv layer, and the fully connected layer. But before we apply the activation function, I think when you're in the lecture, you will actually understand what batch normalization is. It's basically we're normalizing the data after in batches. A batch size doesn't have to be too small so that there is no effect, and it doesn't have to be too large so that our data isn't our data isn't drifted. When we talk about batch normalization in CNNs, we will go the same steps that we've done previously. We'll have to recap them. It's not about just of a difference, just adding about two steps of code. Again, we import transforms, we import torch. We are able to where we transform and we normalize, in which we convert the image or the numpy array into a tensor, we normalize the standard deviation and the median. We download our data set. We load the batch size of 256 on the train loader. We have already created our class net, which is so now here is what we do. Like I said earlier, in the LeNet architecture, we're applying batch normalization after every convolutional layer and after every fully connected layer, but before we apply the activation function. So we have our self.conv2d, which is the first convolutional layer, our average pooling layer. We also define bn1, which is our first batch normalization layer. Now we define this batch normalization layer, which has an input. The output of the convolutional layer 1 goes into this batch normalization layer. That hence it has the input as 6. Then we again define the convolutional second convolutional layer, batch normalization 2, where we get the output of conv2 into the batch normalization of 16. We then define our fully connected layer 1, 2, 3, and correspondingly for layer 1 and layer 2, we're able to get a batch normalization layer of 120, batch normalization layer with an input of 84. Now, while this is how we've defined all our kernels, and now we'll arrange them. So again, following the rule, batch normalization in LeNet is provided after the convolutional layer and before the activation function. So we take our input image, send it to the first convolution layer, then send it to the batch normalization layer. Then we apply the activation function over it, and we apply the pooling layer over it. This goes into the second convolutional layer. We apply the batch normalization layer 2 over it, activation function, average pooling. Here like in the earlier example, without the batch normalization, we have seen we flatten it to convert this, which is a 2D image array, into a 1D array, which will be used for our fully connected layers, where we take the fully connected layer, apply batch normalization, apply the activation function. Similar for the second layer, and it's for the third layer, we do not need to perform the activation because finally we just require the output, and we get our output return. Is the output that is returned is the final. Require this. Again, we define the we define our what we call our loss function and an optimization function. This is similar to what we did previously, and we load our data set. Again, everything is similar. Just the only difference was with batch normalization, we're adding it up here. So this is the sample image that we have taken, and it is able to provide an output of 8, which is what the sample image asks for. So this is what how you apply batch normalization to a Linux architecture. Um, so now I think Deep will be taking over modern CNNs. Does anyone have any doubts that, or any questions, or you want me to cover any part again? Because I'm there till the end also. So
Ananya, I think we have a question in chat. Um, Hello, am I audible?
Yes.
Yes, yes, you are.
Yeah, so the bias is set to false in conv2D because the because before doing batch norm, it is kind of considered a standard practice to remove bias because batch norm cannot uh, um, cannot perform on the bias is equals to true thing. So that's why after passing through a conv2D layer and then going to batch norm, we set a bias to false. Does that solve your query?
Yeah, I understood. Thank you.
Yeah. I think Josh will be taking over now and starting with modern CNNs.
Yeah. Once. Is my screen visible?
Not yet.
Once. Is it visible now?
Not yet.
I'll rejoin. One second.
Also, to further clarify on Shrey's doubt, we don't use a bias in Corn2D because, according to this paper of batch norm, they say that they have an extra parameter in the nn dot batch norm package, which is called beta of batch norm, which acts as the same thing of what bias does. So that's why we said the bias false. Just your screen is visible now.
Finally, thank you. Yeah. So today I will be covering modern CNNs, and these are the set of topics I will be covering. We will go through the LXNet architecture, VGG architecture, Google LeanNet architecture, ResNets and DenseNets, and I will be showing you the implementation of VGG, inception blocks for Google Nets, and the residual block for the ResNet architecture. So uh, this is just the setup, and we are not using any memory for now. So at the left, this is the LeanNet architecture which we just saw, and on the right we have the LXNet architecture. So if you see the LeanNet architecture, LeanNet paper came in 1989, and the LXNet paper came in 2012. And in all these 20 years, if you see that we have only added a few layers and made the network deeper. This is because in the previous years, like after the LeanNet model came out, most of the researchers or the scientific community focused on the manual feature extraction, and they uh, tried to slightly improve the feature extraction pipeline rather than concentrating on the actual architecture. And then came this researchers like Jan LeCun and Joshua Bengio and Andrew Ng, who thought that we should not concentrate on manual feature extraction, but we should let the model learn the kernel functions by itself. And that is when the modern CNN phase started. And the main difference between the LeanNet and LXNet architectures were that the LXNet architecture was an eight-layered architecture. And if you notice in LeanNet, we use sigmoid activation functions, but in AlexNet we use ReLU functions as activation functions. And why this mattered a lot was, if you remember in the sigmoid activation function towards the ends, we have like at 0 and 1 we have a flattened structure, which is why the gradients go to 0. And in ReLU, that is not the case because the gradient is always 1 if the value is positive. And in the like in 1990s, LeanNet architecture was there, but it did not give very good results. And the SVMs during that time gave better results. This is because the GPUs were not powerful, and even like variants of stochastic gradient descent or this activation functions were not yet introduced. So we will not code the AlexNet model, and we'll move to VGG now. So this is the AlexNet and this is the VGG model. In VGG model, what we have is VGG blocks. These blocks keep repeating themselves, and at the end we have three fully connected layers. Uh, so if you, like this is the VGG 16 architecture, and VGG 16 came in 2014 if I'm not wrong, just after the AlexNet model. And here, if you see, this is the image. We have 224 into 224 pixels, and we have three channels. That is the RGB values. And then if you observe, we try to reduce the size of the images. Like from 2 to 4, we go to 112, 56, 28, 14, and then 7. And we increase the number of channels from 64, 128 to 56 till 512. And then at the end, we flatten it and we feed it to the fully connected dense layers. And then we apply a softmax layer at the end to get the final output. So we will now see the implementation of VGD. This step is this block of code is the same as the one we used earlier. The only difference is this transformation. And VGG model requires large images as inputs. So in we like transform the images to a size of 2 to 4 into 2 to 4. And then we'll first code the VGG block, which is here. And then we will repeat those VGG blocks and add the fully connected layers to make the VGG architecture. So we will define a function called VGG block, and we will take as inputs the number of convolutions, input channels, and output channels. So here in each VGG block, you can have different number of convolutional layers, but all of them are 3 cross 3. So the kernel size remains the same, but you can have the different number of convolutions. So we will take that as input, and we will define this empty list layers, and we will append every layer to this list. So then we will run a for loop for as many times as the number of convolutions, and each time we will append a conv2d layer with kernel size 3 and padding as 1, and the input channels and output channels are same as the ones we get in the input. And after each convolutional layer, we apply a ReLU activation. Like I mentioned, now we don't use sigmoid activation, instead we use ReLU. And then we set the input channels as the output channels. This is because the output of the initial layer is equal to the input of the next layer. So once this runs, we will have a list of, we will append the layers to this list. And then finally, if you see here, we have a max pool layer which tried to at the end of each block. So we will add that, we will append that to the layers list, and we will return nn.sequential. So this is the input we are giving for making the VGG block. So the first parameter here is the number, like the num cons, which is the number of convolutions, and this is the output channels. The input channels is simply the output channels of the previous layer. So we will code the VGG architecture now. And here first initially we will make all the VGG blocks. So we will just append, like we will call the VGG block function, and we will keep appending it to the final architecture list, which is con blocks. And then once we have all these blocks ready, we will go for the FC layers. We have 3 FC layers here. Uh, so this is, two of them are of size 4096, and the final one is 1000. So in this is the architecture which was proposed in the final paper, original paper. So they have kept the outputs size of the final FC layer as 1000 because the data set which they use, which is ImageNet, had 1000 categories to predict, but we are using MNIST. So there are 10 categories to predict that. So we will keep the size of this layer as 10. So yeah, after all the VGG blocks, we will now append the fully connected parts. And this is simply because the output of the VGG block, it is equal to the number of channels into the image size, which is 7 cross 7. And the next layer is of size 4096. So after every linear layer, we apply ReLU and dropout. Dropout is set to 0.5, which means that at random we will drop half of the activation, and we will run this block. And we have our VGG model ready. I'll just print it again. So this is the architecture which we have just made, the VGG architecture, and we will move it to the GPU. And for training, I have used the same blocks which we used earlier. And since VGG is a large model, it will take a lot of time to train, which is why I have just trained it for one epoch. You can train it for as many epochs as you want later. Then came the Google LeanNet model. So now at Google, the researchers were trying to figure out, like, if you see here, the models use kernel sizes of 11, 5, 3, and whatnot. So everyone used the kernel sizes ranging from 1 to 11. And people at Google were curious about which kernel size to use. So while researching about that, what they came up with is, what if we like use all the kernel sizes together? And in the Google Linet model, if you see, there are these blocks which are called inception blocks, and this is the inception block. And here they have used 1 cross 1 conv, 3 cross 3, 5 cross 5. All these are used together, and the outputs are then finally concatenated. So it is important to note that why they are using this 1 cross 1 convolutional layer. This is because this is done to basically reduce the uh, complexity of the network. Because if 1 cross 1, basically what it does is, it does not change the shape of the image, but it reduces the dimensions. Like the number of channels, input channels get reduced. That is why we use this here before the 3 cross 3 and 5 cross 5 convolutional layers. And now we'll see how to code this inception law. By the way, this inception is inspired from the movie Inception. And yeah, so we will make a class Inception, and then we will start from this path. This is the first, second, third, and the fourth path. So for the first path, we have a convolution conv 2D layer with kernel size 1, which you can see here. For the second path, the first we have a conv 2D layer with kernel size 1, and then we have a conv 2D layer with kernel size 3 and padding 1. So that is this. And similarly for the third and the fourth layer, we make the same changes. And in the fourth, we have a max pool layer with stride 1 and padding 1. So then in the forward function, what we do is we take this, apply relu, and we come here. And then similarly, we'll calculate the outputs for all the paths, and then we'll concatenate it. So that is what we have done here. We have taken the input x, applied relu to it. This is the output of path 1. Similarly, for path 2, first we will go through this layer, take the output, feed it as input to this, take the output, and then concatenate it and apply value after each layer. So uh, at the end, like, we concatenate all the results from all the paths, and then we provide the inputs, the number of output channels for each path, which is six, like we have used here. So this is the input we are providing here. This is the architecture which was proposed in the original paper. And so we have, for now, we have coded the inception block, and we encourage you all to like try to code the whole of Google Net architecture afterwards. And we will move to ResNet architecture. So first, like, what was the problem with this Google Net VGGs, and why did we come to ResNet? So like in the traditional architecture, you have this activation for this layer L. You pass it, you get L plus 1, and after 2 layers, you have an activation of L plus 2. So this is the path which your activation follows, basically. So this activation of layer L goes to this linear operator, then we apply ReLU to it, and this output is fed to the another layer. It goes to the same linear operator ReLU, and then we get the activation for L plus 2. So this linear operator is basically weights into the activation plus bias, and then we apply this activation function to get the output. And so this was the like main path or the traditional method. But now in residual blocks, what they did is they introduced a shortcut or a skip connection. So they took this activation and directly passed it here before applying ReLU to the second layer. So why did they do this? So after doing this, uh, this is the equation basically you get for activation of L plus 2. You apply the like activation function to the output of L plus 2 layer plus the uh, activation of layer L, because we are directly adding it here. So why did this work? So this is the traditional thing which we did earlier, and this is after applying skip connections. So in this, if we expand this equation, basically we substitute the output of L plus 2 with the weights into activation plus bias. And if, in the earlier sessions, like we had introduced the problem of vanishing gradients where the weights become zero. So if you have a very deep network and there is always a chance of vanishing gradients, so if the weights become zero, in that case, the whole term cancels out, and we still have this A of L remaining because we have added it to the skip connections, and the activation of A of L is simply A of L. So in the worst case, what you are doing is you are not uh, like if there is a problem with vanishing gradients, then you are not able to learn anything further because you get a zero every time. But here you are getting A of L again. So this architecture for sure does not make your network uh, stop learning anything, but can always make it better because SGD always moves to the minimal point, right? This is why the ResNets were so successful. And now we will code the REST block. So these are just the imports, and we will see like we will first import like we will use super function, and then we will try to code this thing. So there here first we have the 3 cross 3 convolutional layer, then we do batch normalization. Like Ananya mentioned, we do batch normalization before applying ReLU, and then we have another layer batch norm, and then we add this input X directly here, and then finally apply ReLU. This is basically the skip connection. So here first we have the first convolutional layer with kernel size 3 and padding is 1. And then the second convolutional layer is also the same. And we have two batch norm layers. So in forward, what we do is we take the first convolutional layer, apply patch norm to it, and then the ReLU activation. And so after this, if we have given the input X here and we have got output Y. So this X and we are here now, we have got the output Y. And sorry, we are here and we have got the output Y. So we will now take Y, feed it as the input to the next convolutional layer and apply batch norm to it. And we will finally come here, and this is the Y, and we are here right now. So now we will directly append X to this Y because of the skip connection. So if you want to implement this one cross one convolutional in the skip connection, you can directly use this by adding this simple one line of code. Here we have set by default it is set to false. So we are directly like adding appending X to Y. We'll run this. And just to show you the shape of the output remains the same as the input here. And this is the final ResNet architecture. And you can see here the REST blocks implemented again and again, and at the end you have global average pooling happening instead of the FC layers. This is the final FC layer which maps it to the output categories. And finally, the last is the DenseNet. So there is a subtle difference in ResNet and DenseNet, which is in the ResNet, if you have noticed, the skip connections are added, but in DenseNet they are concatenated, as in like you don't add 1 plus 1 2, but you like keep both of these 1 comma 1, which is why the size, because we are not discarding anything or not adding anything, the size increases because and it is like it takes a lot of GPU memory to train DenseNets as compared to ResNets. That is all for my part. We have provided further readings and code implementations of all these models in case you get stuck. And if you still have doubts, you can always come to the office hours. And if any of you have any doubts now, can ask. Oh yeah, I just read the chat and I have the ResNet paper open. So I think we was talking about this. So what they showed is that 50, if you have a deeper architecture like 56 layered architecture, the training loss as well as the test error, it is more than the architecture 20 layered architecture. So just increasing the number of layers does not always help. And this is the final ResNet architecture where you have skip connections everywhere. I see your question. Which architecture is most effective? So that again depends on what you are trying to do and your use case. You cannot say that this architecture will work the best for every like use case, but uh, it also depends on what kind of GPU you are using. Do you have like the GPU memory to, for example, apply denseness to your models because it requires a lot of GPU memory, etc., etc. Are there any other questions?